Hey, here is Miss Sarika with kind of a review of the lab. So just sort of follow along. You can get your page 75 out and see how you did with kind of how I'm going to explain things. So one thing to note, I'm not going to really have the same data that you have, but I'll give you some examples of what you might want to be thinking about when you're looking at your data. So this first section is about gravitational potential energy, and your first IV is the height or the distance. So you should have chosen something like 1 meter and 1.5 meters. Something like that. And if you didn't use meters, make sure you're paying attention to that. Or you could have used centimeters, obviously. So your evidence, you should have had some sort of data for the diameter, and that would have been, the distance across the impact site from here to here. And again, it should be in centimeters. So the question is, what's the relationship between height and the amount of gravitational potential energy? So what did you notice? Well, you probably should have noticed that as the height increased, so an increase in height, it should have equaled an increase in gravitational potential energy. And you probably saw this when there was a larger diameter, as you had increased the height. Something like that. Your data should have supported that. Okay, so the next section is about mass and how we have evidence for the amount of potential energy. So as you were picking your IV, you probably chose 50 grams, 100 grams, and 200 grams. So if you had a different amount of mass, should you have changed the height? And hopefully your answer would have been no, that you would have kept the height the same. Whatever that would have been. Maybe it would have been at a meter or whatever you decided to go with. Now again, you were measuring the diameter of the impact site, and whatever it was, you probably noticed that for each mass, the diameter got increasingly larger. So this relationship question is between mass and the amount of potential energy. So you should have noticed again, very similar, that as mass increases, there's an increase in gravitational potential energy. Now, earlier I mentioned in class about how if you're going against the nature of something, that's how you know that there's more potential energy. So think about this. All of these weights, they don't want to be off the ground. So as you lift them up and increase the height, or if you have a large mass of one, and it's especially if it's large and is going higher and higher and higher, it doesn't want to be there. It wants to go back to the ground. So the more work you have to do lifting it up higher and higher and higher, and so if the larger mass, it's harder to do, obviously, and the higher it is, the harder it is to do, the more you're working against nature, and so therefore it has more of this energy stored up in it because you had to put a lot of that energy into it, but now the object has that stored. It's ready to use it. Let's use the same idea for elastic potential energy. So distance from the starting point. So in each of the classes, I used that large slinky, and you could have done this with a small one. So our data is kind of qualitative for a lot of us. Maybe you measured it, but let's say you moved it just a little bit away. And here you moved it a lot away from its starting point. Well, your evidence depended on, what happened with the size of your slinky, but maybe this only took traveled 2 lengths of the slinky, the wave, and maybe this one traveled 4 lengths of the wave. So for this question, what's the relationship between distance and the amount of elastic potential energy? In this case, as the distance away from the starting point increases, then we have an increase in elastic potential energy. So again, thinking about that idea of going against nature, that the more you pull it away from where it wants to be, that the more it's going to have that energy stored up in it. Same thing about a rubber band. That's another way to imagine this besides a slinky. Okay, next is the ability to compress or stretch. So we had a racquetball and we had the dough, the Play-Doh. So the evidence, well, you could have both squished it, and this was hard to squish, and this was easy to squish. But aside from that, we also could have dropped them to see them bounce. And we saw that this one, the ball, the racquetball, it bounced really high. And the dough just bounced a little bit. So it bounced just a little bit. What does that tell us about the relationship? Well, the ability to compress and stretch and the amount of elastic potential energy. That relationship is the harder it is, harder to stretch or compress, harder to compress or stretch means you have an increase in elastic potential energy. Why is that? Well, think about that idea of the going against nature. If it's really hard to push or really hard to pull, then you have to put a lot of your energy into getting it to that position. Well, it doesn't want to be there. It wants to go back to its original position. So the harder it is, the more you have to work against its nature, the more you're going to have stored up in it. So think about that when you think about like a bow and arrow. If you've ever tried to shoot a bow and arrow, I never have, but I've only heard that it's really hard actually. There's a lot of tension in the string. I don't know what it's called, but there's a lot of tension there. It's really hard to pull. It's not super easy, and that means that the more work you have to put into it, the stronger of a amount of energy you're going to have, which is what you'd want if you were using your bow and arrow. You don't want it to be kind of wimpy. You want it to be able to travel farther. Okay, so now we look at electrical potential, and I'll be honest, the directions weren't quite as great as they could have been, and the more I think about it, there are a couple things here that I want to talk about to help you out. So the first is we're looking at the distance, but I want to break this down, and let's do it when we've got a positive and a positive, or a negative and a negative, and then let's look at when it's a positive and a negative. So we had a couple of things that you could have looked at. You could have used the balloon in the stream of water, and you could have used the pith balls and the straw. And what you saw is as you charged them, they were able to influence other objects like the water or the straw was influencing the pith balls. And so, as you were using these charged objects, they had the power to move the other objects. Here's where it gets a little funny. When the charges are the same, like both positive or both negative, they would typically want to repel, right? So, if they want to repel, then to get more potential energy, we would want to try and put them as close as possible to each other because that's going against their nature. So, if you had anything going away from each other, and it depended on kind of what materials you were using, they would have an increase in potential energy when they were close. Next, they had more potential to move objects. There's more distance that it can go when they're really close. And I'll use another example in a second to help explain this. So if they're the same, they would attract. So they would have an increase in potential energy, in this case, when they're far away, because they want to be close together. So you have to work more to keep them apart from each other. So that leads to our question down here. Can a balloon do more work if the object is closer or farther? Well, the idea with this, and this is where it got a little confusing, if it's farther away, it can do more work because an object is able to move more distance. That means more work is happening. But I also want you to understand that if the charge is strong or weak, obviously if the charge is strong, there's going to be more work able to happen. So this is a little bit funny, but I do want you to understand about the repelling and attracting relationships and how the amount of potential energy does depend on what kind of charges are present. However, when the charges are stronger, then we have more energy as well. Okay, now let's look at chemical potential, and I made a mistake. There shouldn't be a third box here. So we looked at a glow stick, and we also looked at a hand warmer. So these are two different ways that we could see how chemical potential energy was being used. So for a glow stick, we saw that light was produced. That's one way that we'll know that there was a chemical reaction, or that another way to say that is that the chemical potential energy was being used. So for a hand warmer, we had heat was produced. But there's also a special way that we talk about heat, and in this case, you do need to know that it's also called thermal energy. Okay, that's an important thing to note. Okay, now our next question is, what evidence do we know, or do we often see that shows that an object used its chemical potential energy? So in this case, we saw light, we saw heat or thermal energy. But there's some other ones, and I just wanted to jot these down, and you might want to add these too. A lot of times there can be a sound produced. There might be an odor produced. Think about if you burn something in the oven, you definitely know that there's been a chemical change. It's very clear. It could be bubbles in the creation of a gas. So think about baking soda and vinegar, for example. The biggest one that you need to know, though, is heat. Heat is the most important one to understand that thermal energy is often a byproduct of chemical reactions. Okay, the next question is, what does chemical potential energy depend on inside of an object? And if you went back to your notes and you looked at this, chemical potential energy is going to depend on how atoms are arranged. Why? Because in a chemical reaction, they rearrange. So all of this energy that we're talking about is dependent on the fact that atoms are arranged in a certain way. When they break and change, they release energy, or they use energy. So knowing that in a chemical reaction, they rearrange. Okay, so now we're going to look at magnetic potential energy, and it's very similar to the ideas from electrical potential. So for this one, this could be a north-north, south-south, and this would be a north and south. So if we had two magnets that had same poles, and these are not charges but poles, these would repel and these would attract. And the same relationship goes here. So if I have these two magnets together and I want to increase their potential energy, where should I put them? Well, if I'm going against their nature, they want to be apart. So if I put them really close together, and I'm sure you probably tried this before, hopefully in the lab, when you put them really close together, you notice that if you let go, they shoot apart from each other. You've given them a lot of energy because you had to force against their nature to get them there. So when they attract, if I want to increase the potential energy, in this case it's the opposite. I want them far away from each other. When they're far, I've had to work to pull them apart. They don't want to be apart from each other. They want to be together. So all the work I had to do to force them to go against their nature, that's what gives them a lot of energy. Okay, our last couple questions here. Can a magnet do more work if they're closer or farther? And can it do work if the object is a metal? So obviously, the farther they are, usually the more distance is traveled. Again, it gets kind of funny when we talk about the different poles, and you need to be aware of that because you will see something like that probably on an assessment. But we're thinking about the material. Most, not all, but most metals, a lot of them at least, are going to be, well, actually maybe not a lot of them, but they can be blended together. So a lot of different combinations of metals can be magnetic. And the idea here is that if the object is not made of metal, like it's a piece of paper or wood, you're not going to have a lot of energy related to that. So there's not going to be a lot of work. So the type of material is important. So overall, check how you did, make some changes, and note that if you go against the nature of an object, that's where you're going to have more potential energy. Equals more potential energy. And that's kind of a big theme that you'll see when you look at all of these. Okay? So check your lab packets, see how you did, make changes that you need to, and feel free to go back and listen to a section again if you need a little help. Okay?